with
That's not right. That's not right either. I have no idea where it is. We're just gonna do this with Mike Dave.
With Mike
And keep on saying stuff.
and Tony and Jay.
Yes, hi. It's Issuenite.
Where's Jay?
Jay, where'd you go, Jay? Yeah. Tony, I came out. I gave my kids a bath.
Yeah.
And I came outside, and usually Jay's here, but he wasn't today.
Oh. So where is he?
I don't know.
Okay.
And so I called Mike D. Hi, Mike.
Hey, Mike.
Not accused with Mike B. I called him to find. He's a physicist teacher. You don't tell us where, but you teach physics.
I teach physics.
What kind of physics?
I teach high school physics, Regents.
New York State Regents?
New York State Regents physics, and I'm well qualified. I've had an entirety of 24 college credits in physics.
Excellent. Now, so
Because there's got to be a logical scientific explanation on why Jay's not here and where he is.
That's
right?
exactly. So we're really going to homeschoolers, you're going to want to mark this episode down. We're going to talk about physics today. You can use this to help you earn your Regents or to find lost friends. Right, Mike?
That's right. Lost friends.
Where do you want to start, Tony? What's our first theory on
well, I mean,
where is
there's
Jay?
lots of possible theories. I mean, my first thought is if he's usually here, right where you are, and he's not, he may be, maybe he was transported away.
Okay. All right. So would that be a transporter?
Like transporter, teleporter,
okay. So
digital conveyor.
We'll call that teleporter.
Teleporter?
Theory. Okay, let's get into teleporter. Now we can start simple. I think we should start simple, Mike, because it seems like since you're New York State Regents, we may have to start simpler. So I'd like to start with, well, I don't know, teleporter. How's that works, Tony? I don't even know how that works.
Well, there's different theories according to this AI thing on the computer. There's the quantum teleportation. There's the scanning and reassembly. And there's the subatomic particle theory.
So, like in Tron, it's scanned them one line at a time. Is that what you're scanning like a fax machine, right? Teleportation.
Well, I think regardless of which one, it takes a scan of you and itemizes every bit or part of you, and then sends that information somewhere else, and that other somewhere else reassembles all those parts.
Okay. Right,
like a 3D printer.
Like a 3D printer.
Ooh.
Well, I guess. Let me just see if I have. Let's see here. Yeah, there's all of us. So this is like this, Tony. He just. There's just a wormhole.
That looks like somebody falling through the ceiling.
Okay, maybe that's not a good one. Let's try
that's
this
more
one.
like
Okay, this is more like Star Trek.
Oh, okay.
Right, so it's Star Trek. Is that, Mike? Is that actually even possible? I mean, can they dematerialize? I mean, is it a subatomic level? Is it what level is it? What about like quantum entanglement? What about all that stuff? I mean, how's that work? Do we know anything about that? Is this way above New York State physics or?
Well, this isn't exactly what we teach in New York State.
All right,
physics.
show me what you teach.
We teach 90% of the year is 60% of the year is mechanics, which would be the classical physics that we know. We do understand that there's a relationship between energy and mass, right? So it wasn't until recently, in the last 100 years, that we realized that mass and energy are interchangeable. Like mass could be changed into energy, and it seems that energy may be able to be turned into mass. That's the tricky part, really, that you can turn energy back into mass.
So is that E equals MC squared? Is that?
Yeah. A little bit of mass makes a whole lot of energy.
So where is that from? Do we have that?
Oh, I have that. Yeah. That's in, like I said, the last 100 years. So that's in the modern physics portion of the reference table. That'd be right here.
Okay.
E equals MC squared. Right there.
So E is energy.
Right.
And it's pure energy. Versus mass, pure substance.
Material substance, yeah.
And then you got this random speed of light thing.
Yeah, c is a huge number. It's the speed of light of the universe. It's like 30 million meters per second.
So it's a constant. That was what the
It's a
C is, right?
constant,
And for some reason it's squared. We have no idea.
Yeah.
It's exponential. So energy. So increase energy, the mass increases, or vice versa. If your mass increases, the energy for what?
Vice
By a
versa.
lot. Yeah, the energy.
What is increasing?
The mass, the energy. Okay, so if the mass was completely annihilated and turned into energy, that's what annihilation
I
means.
see what you mean.
Nihil, nothing becomes
nice.
nothing. So if the mass becomes nothing, it turns into energy, and it becomes a lot of energy.
So
Okay,
that-
if
so
the
we
mass
might-
becomes like a black hole, a mass is nothing.
No, that
No,
wouldn't be a
that's
black hole.
that's
That'd
not a
be the
black hole,
opposite.
no.
What?
Black hole is lots of mass. This is no mass.
Oh, I see what you're saying.
Yeah.
Yeah, I was
so,
thinking also, yeah.
so if J weighs, I don't know, however many pounds or kilos or whatever, and he converts to all energy, how much energy would that be?
An immense, insanely large amount of energy. Like, because
Okay.
1 kilogram could power the city of Chicago for like a decade.
1 kilogram of what, J?
1 kilogram of any mass that was converted completely into energy.
So
would
one
be-
wow.
kilogram of J could be solve the energy problem.
Yeah.
Well, isn't it? And when you split an atom, is that that's releasing energy, right? It's converting. So that's what you're saying. There's a pure conversion of mass to energy. Is that what you're saying?
This is pure.
Okay.
Pure. So when you split an atom, you still have some energy left, but the little bit of energy that was removed from splitting the atom
What?
becomes energy, a lot of energy.
And
Even
the-
a little bit becomes
Right.
a lot of energy. Yeah.
and
So,
dissipates.
so Jay seems like he's a pretty energetic person at
He is.
times.
Yeah.
So will that affect the transporter? Getting back to that, if you're putting a lot of energy into the transporter, I mean, you're breaking up particles. So
You're not
does
splitting.
energy.
You're not splitting J. Or you're actually splitting atoms.
Well, you're taking, according to the transporter theory, you're taking bits of J and
Yep.
breaking them up
Right.
a million times or whatever.
Trillion.
You're breaking it up
really?
to create energy, and you capturing that energy. Does J become light?
Well, no, actually, he's got to become energy, right?
It becomes energy. Yeah.
Becomes
And
energy.
it would be light.
Right,
Yeah.
right.
Either.
Because in order to
Visible or
become, you
not
have,
visible.
in order to go that. But I don't know what that means. Are you traveling at a speed then? Once you're light, you don't want like to lose parts of J because he's emanating like a flashlight.
Right.
Oh, there's
Well,
J
that's
on the
the tricky part, I guess, would be directing that energy, right? Like up into whatever vessel
Getting J energy all down to the planet
or
or up to the wherever.
wherever you want to channel that
Right,
energy.
or wherever
he
went.
Send the
Yeah.
J energy.
But he would be traveling at the speed of light, though. It's a
Right,
problematic.
super fast.
Unless you
Right.
could create a warp tunnel as Jay's traveling, right? So travel faster than the speed of
Right.
light.
Right.
His light. I'm not talking about ship.
Yeah.
I'm talking about his energy. Warp tunnel.
Yeah. So it's
Energy.
not just a digital. It's not a 3D printer. We're not taking the information about J and then printing another J.
Right. It is J.
Where it is J. So
Yeah.
we got to actually
Well, you got to convert back.
We got to We got to convert J to energy. Some of them is already energy,
It may have happened.
but the
Right.
the part that's not energy. Well, even the part that is energy, we've got to like make faster energy out of them.
Yeah. Yeah. And you have to conserve it, right? You can't have this energy leak
Oh.
anywhere else
J
because
would be
parts
leaking
of
all over.
Parts of J would go
Right.
with that energy. Right?
And
So-
also, if you're going through certain things, like it can't be light. If it's light, then it's gonna reflect or things. We need to convert an energy that's safe enough to travel through space. Gravitation. I don't what goes through everything. Like the sun has particles that go through it. We need to track. J
Well-
probably was converted to something that because assuming he went I don't know who
why,
did this.
Why can't it be regular energy?
Light.
Well, visible or not visible
Because-
light.
because-
as long as there's no planets in the way to
What if
wherever
there's
he's going.
rocks or little pieces of dust? It
Well, I
stops
mean, you're
part of
going
his
to
colon or
lose
something.
little bits of him here or there, I would think.
Well, I'm worried about that.
Yeah.
Concerned about that.
Yeah.
Even quantum energy, quantum computing has there's errors, but they're able to correct them.
But
I
we got
guess
errors anyways. Like, isn't there biological errors from when our cells
Yeah,
reproduce
like-
or whatever?
Oh, sure.
Other-
Every time we have a reproduction, there's an edit that's occurring
True.
somewhere
So
in
my
our DNA.
cells split and there could be a
every single time.
Mistake.
Yeah, yeah, for
Okay.
sure.
So, I mean, you do the math and, what has more.
you got to figure it out. Is okay. So he's okay. Just for a second, He's being transported. He's changed into energy. He's
Right.
moved into. I don't know how long that process takes. In that moment, he's
Very
not
fast.
growing. Right? He's not growing. Jay's like
it does seem
stuck
like
in
there'd
time.
be a still, yeah,
Wouldn't it be a glitch in the right?
in the time
And
space
if,
continuum
and if
for
you let-
him.
yeah, but if you didn't convert it, if you held on to that energy for a long time, he would be just stuck.
Like if you held all that energy in a jar, held the J energy
Yes.
in a jar,
Jay in a jar.
Mm-hmm.
and
J in a
then brought him back, and he wouldn't. Would he know that time passed? Or not?
I don't think so.
He would not know.
Well, he'd be traveling the speed of light, so doesn't that affect
Right.
time?
Well, he's not
Right, that's
somehow.
exactly
Again,
right.
you're not going to be able to do light. I can't foresee light wastes energy. Light photons hit something and it ends. We need to get him a stable form of energy, don't we? Isn't light it's once light hits, the photons hit. What happens to it?
Well, I mean,
Well,
we're looking
it's
at
gone.
billion-year-old light from
Right,
through
but
the
then it gets
telescope,
here, and
right?
then what happens? And it's gone. I mean, hits your eye.
It's your eye.
Mm-hmm.
Well, we need it to hit something that we need it to hit the other end of the transporter mechanism to reassemble.
To
him.
reassemble him.
Yeah.
Just want to say our first comment here. Grace D says, "I know him."
Mm-hmm.
So I'm not sure who says
Jay.
him. Maybe Jay.
She
No,
knows.
it was Jay,
Yeah.
I think.
Yeah.
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 Okay, so Tony, we're
I
gonna
do have a separate comment from.
okay. We just want to let you know we're talking about Jay's missing, and we want to know where Jay is. And we asked a resident New York State Regents physicist, actually just physics teacher, Mike D'Alessandro. Oh, I just said your last name, but that's okay.
no first names here.
No, yes.
No middle names.
So we asked him about exactly how could this happen. I'm interested in physics. Maybe this can help to explain things. I don't want to go anywhere else where you don't want to go. I'm going to talk about like just simple stuff, Mike.
Right.
So like why I'm in space, I'm floating in space. Why do I keep on going? Why aren't I stopping?
Well, why would you stop?
A force maybe stops me.
Right, a force, an unbalanced force would stop
Okay.
you. Right, otherwise,
A
materials.
disturbance in the force.
There's
that difference?
Exactly. Well, a force.
A force.
An
Okay.
yeah. Things tend to do whatever they've been doing. Right. They never stop doing what they're doing unless there's a force. Right?
Okay.
So that's the attitude you need to have. That's the way you need to come about this.
In life or just in space?
Both.
Yeah, okay.
I think,
Yeah,
yeah. But
yeah.
mostly in space.
Right.
So if you set something in motion, it's going to stay in motion, right?
Okay.
If you stop it and keep it at rest, it'll never move unless something applies. a
Okay.
force
Let's go
from
another
outside.
step further. Does an object at rest stay at rest?
Yes, objects in rest
Relative to what?
relative to all other matter around it, unless it is affected or pushed on or pulled on by an unbalanced force, right?
So I'm here
Mm-hmm.
and I'm holding steady, but meanwhile that planet over there is moving away.
Mm-hmm.
How do I know I'm not a force wasn't on me? How do I know?
well, you have a lot of forces on you right now. Currently, you have tons of forces.
Yeah, I
on
got
you.
9 kids. It's true.
Yeah, right. Well, you have Earth pulling on you.
Okay.
You have a chair
Well,
pushing
let's
up on
say
you.
I guess things have forces from far away. Like even if a black hole's way out there, it's exerting force on me, right?
Yes.
Is there a point where it's not exerting force on me?
No,
Based on
because gravity has no limit, right, to its
You
distance.
go on.
So the
What-
universal gravitational formula.
we think
Find that way.
there's some theories out there, right? That
Right, I guess.
that
yeah.
it? What is it? Okay, I see.
So this is the formula, right? You got the force of gravity is equal to some universal constant, capital G, and then you got the mass of the two objects, mass 1, mass 2, and then it's all over r squared, right? So that r represents the distance between the center of those two masses, right? So that number can never be 0 mathematically. If that number is 0 mathematically, if you put a number over 0, you
It's
get your error.
undefined.
Yeah, it's undefined, right? It's an asymptote on a graph, right? So no matter how far we move two objects from each other, there's always a force, no matter how small. It will be very small, but there's
So
always-
am I exerting a force on Jay right now,
You
wherever he
are.
is?
You are wherever he is.
Wherever.
If he's mass right now,
Right.
If he's
Oh.
mass,
Well, how would he not be mass?
how about if he's energy?
if he's energy,
if he's energy? That's not mass.
Well, doesn't mass bend light?
Yes, exactly.
mass does bend light.
So,
So
it's
that-
effect on it. There's nothing. There's nothing that
though?
can't
No way
be
not to affect J.
unless you're on the out. Yes. Is there no way not to affect J unless you're in somewhere in space where there's no space? Maybe at the edges of the universe.
Well,
if the universe is
there's
being
always
created.
space where there's space.
Right.
Well, what if I don't know? What about I don't want to get too much into the Big Bang, but if there's explosion, you have the outer edges of like where there's nothing, truly
beyond
nothing.
the outer edges.
Beyond
You
the-
think Jay's out there?
Well, if he is,
Yeah.
we have no. I know if we can't exert any further.
Now Jay's not here, so I feel like it behooves me to
Behooves?
remind the kids at home not to try exerting forces in places where there is nothing, or trying to transport their friends and convert them to light.
Right.
So
Agreed.
just a little reminder there.
Yeah. So back to gravitational awareness. So I'm in space, whatever, and so you're saying these two, no matter where they are, they're going to exert forces on each other, except for like quantum physics, where you have quantum entangling of two photons, right? That are one. Is there any kind of is gravity affecting those? Like if I'm doing if I have a photon here and they're quantum entangled, there's one way over here, and then I'm able to move this, and this spin happens over here. Is gravity affecting that? Is that completely
It's
independent?
not caused by gravity, but those two particles can
affected by,
communicate.
do you
to
think
each
they're
other through
affected by gravity on a subatomic level? I don't know if they are.
Yes, no matter how small the mass, right? If there's mass, two massive objects, no matter how large.
Well, do they have
If
mass?
there's a
That's a good
value-
question. Do they have mass?
Sure, they do. Particles, like
Photon.
a photon.
Does a photon have mass?
That's an interesting question. They don't necessarily have mass, but they have momentum, which is a conundrum, right? So so momentum is an interesting formula. It's this one here: P,
Let me get there.
lowercase p,
Okay.
equals mass times V, right?
A lot of math.
So lowercase p,
Others.
momentum.
Math.
P
Yes.
means momentum, right?
Yeah.
Because you can't use M for momentum because M is for mass. So they just
Right.
P,
They ran out of letter.
right, ran out of letters.
So
So
P is momentum.
P is momentum,
Momentum equals mass times what?
velocity.
That's a V.
Momentum.
Yeah. So
Momentum.
Gotcha.
So the mass is velocity, mass times its velocity.
Is momentum an It's different than acceleration, right?
Correct. Momentum is a property it's a vector, property of matter, really. Yeah. So,
Wait, I don't know what momentum is. I still don't understand.
so momentum is a quantity. It's a mathematical quantity that's associated with an object in motion. So if an object has motion, massive object has motion, it has momentum, right? So
That's the speed it's currently going. It's got energy, stored energy based on the
right. So when you
velocity.
think about it, like if you look at that relationship there, if you have like a super tanker, like a really large ship that's only moving like half a mile an hour, it has a lot of momentum. Like the ship that ran into the dock in Baltimore, the bridge in Baltimore, and knocked it over. Like that was moving really slow, like less than 2 miles an hour, and it did all the damage.
Yeah, it looked like it was slow motion. Like,
Yeah. But if somebody that like our size needed to have the same momentum as that ship, we'd have to be moving very fast because we're very much smaller.
So
we
for
have to be going
me
fast
to knock down a bridge like that, they'd have to shoot me out of a
really fast,
particle cannon.
really
kind of
really
thing.
really
Okay.
fast. Yeah, particle cannon. Right. Yeah, yeah. But the interesting thing, we came to this topic because of momentum. Particles like photons, which is light.
Yeah.
A photon has momentum, but yet it doesn't have mass. Very interesting.
So it
idea.
doesn't have
It
mass.
does not have mass. Particles.
But it can be affected by gravity, though.
That's right. So they can be affected by gravity. They don't have mass, and they do have momentum.
Is that because time and mass are intertwined, just like a bowling ball going across the five-vector of time, and can bend? The bowling ball, like you can bend it based on like going near a planet or going through a really big planet or a black hole. Time slows down.
I'm actually wondering about that because Jay was kind of experimenting or talking
With
about
bowling?
with black holes.
Oh, okay, gotcha.
Yeah, he was talking about swallowing.
We did talk about swallowing a black hole.
swallowing a black hole. So that would be kind of the opposite if maybe Jay didn't become energy, if he became part of a black hole.
If he put his mouth around a black hole, you would think that the insides would be sucked in.
The inside of his mouth.
It was, yes, kind of. Well, hopefully
Right.
that didn't happen, but
So I'm a little less optimistic. Like with the transporter, he's energy, and you collect that energy, and But if you become a part of the black hole, don't we lose all information about Jay?
Well, I think they've
Or does
proven
it?
that that energy can escape a black hole. I mean, there's certain kind of leaking. It leaks.
Right.
And, bleaks.
But can any of that leakage be J again, or
That's scary. Scary
It
thought.
could. I mean, I suppose it could.
There's a Jake Schub's question. Answers question: if x equals y, but light equals momentum, then what does physics have to do with it? X equals y, but light equals momentum. I don't know what I don't know what x is. I don't know what
It
y
depends on
is.
what X is.
It does depend on what x is.
Well, maybe it's X is J. Well, no, J would be J.
It's a
Right,
good-
J would be a letter J. Yeah.
Yeah.
I don't know. Is there anything else here that applies, Mike? And I'm trying to. Well, we're trying to determine what. First off, we don't know how he disappeared. Was he
Yeah.
teleported? We talked. Wormholes. We even got into that stuff. Tony, you mentioned string theory. I don't know. Is there anything you want to?
Well, I mean, either if you swallowed the black hole, maybe we should be looking on the ground because it's probably very heavy.
Right.
But if it's not that, string theory could bring an explanation. There's a couple different string theories. So the M theory is a hypothetical version that requires 11 dimensions. Bosamic string theory is 20 dimensions of space plus 1 of time. And string theory with fermions is a version that also requires 10, including 9 spatial dimensions. So, he could be here in time, and we know of 3 dimensions, right?
Mm-hmm.
But if there's some hidden 4th through 20 dimensions, he could be around the corner at one of them, right?
Yeah.
I mean, do we know how these strings become new dimensions, or is that not part of high
It's
school?
yeah, we
physics?
don't teach that in high school.
Oh.
Sadly, mainly because we don't know it and it's hard to describe as a society. We really don't. But am I wrong in that?
Yeah, no.
That the 4th dimension is time.
4th is time,
Okay, all right.
and then 5th through 20 is what?
I mean,
I'm not sure.
how do they? Yeah, how do they
Strings?
stop at 10? I mean, like why not 11 or 9?
11, yeah. 11 would be more.
Mm-hmm.
Yeah.
So these other dimensions, they're speculated because they work out mathematically, but we just can't
Right. yeah.
imagine them. Is that what we were talking
Well,
about? Yeah.
we'd have to imagine them because
Right.
we can't see them.
Right.
And we can't see J.
Right.
So it kind of makes sense that maybe he's in one of these strings.
One of
Is
them.
the idea the fact that I can imagine J? Is that make him exist? Is there energy of J? Is that a residual energy? Is there a transfer of energy that happened for me to know J, to have known him, and now he's gone, and now I'm remembering him? Was it an impression it made? Not like a photograph. It makes an impression of a. It's a reflection. You got light, and there's a negative image, and you made a reflection on it. It's not actually J, but was there some sort of not just on a gravitational level, but on a
I do have a correction.
possible.
One of our viewers chimed in. The 5th dimension was a singing group. So we did define that
we
one.
did define that?
I don't
Okay.
think he's in the 5th dimension.
No, I remember that.
I don't think he was. They're tall. I don't think he's that tall.
Right. But 6 through 20 are still up for grabs.
Right. Yep. All right. So all right. So again, this is I don't know if this is how a lot of this is backstory. Mike, I'm trying to understand physics. Do you know? So okay, like mass equals force. M equals Fa.
Yep.
May the force be with you.
Right.
Help me with this one. Mass equals. Did we talk about this already?
Right. Well, okay. So we know that if we go back to the first thing we were talking about, that mass will continue to keep on doing whatever it's doing unless unbalanced forces are applied to it. So that's what we're talking about here. Whenever something stops doing what it was doing, we call that acceleration, right?
Okay.
So an object will stay at rest unless we change its speed by applying a force, or it'll keep going at a constant speed unless we change its speed by applying a
So
force.
if Jay jumps on a trampoline,
Right.
he goes up in the air, he'll keep going up unless something works against that.
Right.
Okay.
Which is
Okay.
traditionally gravity.
Let's
Okay.
just
Yeah.
change gears to Star Trek for a second, or Star Wars. So in this one episode I just saw, this ship was going, and they had this other ship on its tail, and they're going to run out of fuel soon, right? Well, in space, if the object's going, You're not going to run out of fuel,
It'll
right?
make
Exactly. So they must have been. This one must have been accelerating, and this one must have been accelerating.
Yeah,
right?
they're both accelerating.
They're both accelerating,
Correct.
and they're using fuel to accelerate. That's
Correct.
the only way. They didn't say that, but that's right. I'm
Right.
just
That's
trying
the
to-
only thing they could be doing.
The only could they be
right?
doing.
'Cause
Otherwise,
there's no force acting against them
right.
in space, right?
Right.
So
Or
if-
very little. You got distant planets, like to your point.
right. That's
Yeah.
very little, negligible force,
Hmm.
considering we're dealing with the thrust of a spaceship in the opposite direction, right? So what we're dealing with, it's framed in this way on a reference table.
Let me get there.
We frame it. If you look at the
Oh,
pointer
sorry.
here, it says acceleration
Yeah.
is the net force over m, right? You're familiar with it being force equals mass times
Yes.
acceleration. This
This
is
is
a
division.
mathematical.
Acceleration equals F divided by M.
Right.
Okay.
Newton defined force as the rate of change of momentum. When this is Newton's second law of motion, right? So what we're saying here is that acceleration is proportional to the net force that's applied to a mass, right? So if the net force is large, the acceleration will be large. If the net force is small, the acceleration will be
Okay.
small, right?
So J's kind of small, so maybe it wouldn't take a lot of force to move him.
That's right,
Okay.
right, or to change his motion.
Now,
It changes direction.
Isn't there a coefficient for to get over a friction? So there's friction involved, right? So, but
well, if there's
right?
other material,
There's other material, and you got to start putting force on something like
Mm-hmm.
this cup here, and then I got to push it, and it's the friction on the ground, so I got to overcome that. Right?
That's correct. Yeah.
So is there a formula for force when it just overcomes that? When does force start acting? It started acting right away, but it's potential. It doesn't become kinetic until you've reached that.
That's correct.
That threshold, right?
We call that static friction. The friction that holds something in place before it moves is called static friction. And then once it starts sliding, we call that kinetic friction.
Okay, so
I have noticed
Yeah.
that
Yeah.
playing hockey against
Yeah.
Jay, like
Yeah.
floor hockey. Like when you first hit him, he doesn't move too good.
Yeah.
right.
I mean, he's pretty
It's true.
he's
Yeah.
low to the ground.
Yeah.
I've hit him too.
But once you get him moving and sliding, then it's easier to keep going.
Yeah, you notice that
Right.
whenever you push something, when you get it going, you need to apply a much greater force because that static friction is so much stronger. Once you break these little bonds, these electrostatic
Right.
bonds between J and whatever surface he's on,
Yeah.
he'll move a lot
Right, but
better.
so when you
with
say,
less
though,
force.
So overcoming friction, that force though, is that the formula works when it's already moving, or does the formula work when you haven't overcome static yet?
The force equals mass times acceleration, or
I'm saying like there's two different formulas we're having here. They're competing, right?
Right.
You got one that's force equals mass times acceleration. Okay, so now I'm putting a certain force on it.
Right.
But until I got over that initial static
Right.
connect,
Right. There will.
when does the formula? When is it valid? Is
It doesn't
the
begin
whole time?
until you start accelerating, right? So,
Oh, the force doesn't. But you've already
Correct.
put amount of force on there. So
Correct.
isn't that
right. So, like,
counted for somehow?
so here's the deal, right?
Yeah.
So if we have like flat surface and J on the flat surface, and I give J a push,
Yeah.
right. The friction between the flat surface and J actually changes. It'll get large if I push a lot. It'll be small if I push a little bit. But there's a threshold. There's a maximum amount of friction
That's what I'm talking about.
that can occur, static friction. There's a maximum amount of static friction that can occur between J and the floor.
Right. But what I'm saying though is that formula, math, it's not going to start accelerating until we've reached that threshold.
Right.
So there's a formula is suddenly taking action once we've overcome that initial.
That's correct.
Right.
Right.
So it's not even. We're not even talking about it.
right.
The formula doesn't even exist until it starts moving.
Right. There has to be motion, right?
There has
so
to
you
be
can
motion,
push
okay.
and push and push and push.
So
But as long as I'm pushing, there's not a net force, right? There's a force forward in that direction, and there's a force backward on J.
But there's energy being transferred at that point.
No, well, there is energy being used, but there's not being energy transferred into J because energy is work being done, right? And work, if you look at
Let
our
me get there.
formula here, if I go back to the formula, work is
I get there. La, 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 la. Yeah.
the force applied to J over a displacement. You need a displacement to be done in order to increase kinetic energy.
What is
of J.
displacement? Movement?
Movement. Yeah, a change of position from
okay.
one position to another. Yeah.
Again, relative to what? Again, I know we're talking about,
There
theory
has to be-
relativity.
There has to
thing.
be a fixed position that you're comparing the two positions to. So it can be where he was to where he is, or anything else?
So a little bit different twist on this. How's gravitational waves fit into this? So been hearing a lot about this.
Explain what a gravitational wave is, Tony.
I don't know. So they've been measuring these things, like when two black holes collide, or things of almost that weight or size. Yep. It sends out the gravity waves. They propagate throughout the universe at the speed of light. And, I know Jay's played around with surfing a little bit.
Yeah.
So, I mean, is it possible to catch the edge of a gravitational wave?
They've measured. I think they've measured them.
Yeah.
Suddenly.
Right.
They figured out, and they figured out the speed of them based on, I think they had two binary stars or something happen at the same time. And the light reached us at the same time as the gravitational energy would reach us.
Usually they send a laser beam from here to there and then back and then around the corner this way and that way.
Yeah.
And when they return at slightly different times, they know that a gravity wave passed through.
Right.
And then they could figure out which direction it came from and where the black stars are. And I'm thinking if you somehow know that this thing's coming and you can hook up a gravitational surfboard, maybe you can ride it off into the sunset.
So you're thinking that's what happened to Jay, or?
Well, I know he likes to, play around with this surfboard stuff.
Right.
So it's not out of the question, and I know he's up on.
But wouldn't he need like superpowers in order to like breathe in space if he's
Well, yeah, I mean, hopefully he would account for that, but if he's moving at the speed of energy or speed of light on a gravity wave, he'd be energy at that point.
Yeah, I don't think he wouldn't be Jay. He'd be some sort of representation of Jay.
Well, he'd be J energy instead of J mass.
Right.
J energy.
No, the question is, how does he get off and become J mass again?
Well, you need to be able to receive the energy. That's very dangerous. I mean, you're right. I mean, if you're beaming something.
Yeah, I mean, he lives on the edge.
He does.
Bit, yeah.
He does. But you'd have to be able to receive it. And if you miss it, I mean, it's either energy's moving somehow or if you're, I guess it wouldn't be static. It wouldn't be in a jar of J, right?
Maybe you'd have to get a running start, right? Because you're going at the speed of light. So maybe you use the transporter to get going at the speed of light, and then you jump on the gravity wave to continue to who knows how far.
Warp drive, we talked about this before on the show, but not with you, Mike. The idea, correct me if I'm wrong, maybe this is not New York State regions, but you have an object, you create a warp bubble in front of it to compress time. Obviously, equals MC squared. The speed of light is the fastest you can go. If you compress a space in front of you and you travel that distance, you can go theoretically faster than the speed of light because you've compressed the space in front of you.
Makes
and
sense.
then as you move
so
behind you uncompress space behind you. So you're moving. So it's possible to get Jay's very far away if an alien took him or if there's if I don't know.
I'm trying to understand this. So you make in front of you smaller?
You make in front of you. You're actually, the whole thing's in a bubble. Okay, the whole ship is in a bubble, but you've compressed it in front of you.
In front of you.
And then you're traveling through, and
would you be able to fit through it if it gets too small?
Well, everything's small. It's like Honey, I Shrunk the Kid, small.
Yeah.
Everything's smaller. So here's the distance normally, right? Travel speed of light,
right?
There you go. And then if I compress the space between it and travel faster,
so you're not getting smaller,
and
you're not going in there. You're
compressing in front of you, and then you're going the same speed. And then once you decompress it, you're like, holy cow, look how far I've gone.
So if Jay lives 5 miles from you, but you compress the space between your house and his house,
right?
He could just walk from his porch to your porch
in no time whatsoever.
Step from one step.
Right.
Yeah.
The amount of energy, though, because you'd be almost like a black hole. You'd have to create a little mini black hole to compress. That's what black holes do, where they case all this matter into
but
small.
not too big. Too big.
Too
you
big
could
what?
destroy everything. Too big of a black hole. A mini
That's
black
true.
hole.
A
Small
mini black hole, right?
Mini black
Too big would because you wouldn't be able to escape, or you wouldn't be able to uncompress it.
You just
So you put this black hole between your houses. The poor people between
Yes.
your houses would probably lose
Rip
everything.
apart.
And then he walks. Well, how does he?
If
cross
he
the
drives,
black
it'll go
hole?
faster. Well, I mean, it's
You got to move the black hole out of the way real quick, and then
it's consistently constant velocity. Like it's consistently compressing and uncompressing simultaneously, right?
I don't know.
Yeah, as you're going here, you're short, and then it's uncompressing time. I don't know. That's the idea.
I think that's reasonable.
I mean, the amount of energy you would need would be astronomical. Amount of energy you would need to do that.
Right. You really, like Tony said, you'd probably disturb other people that you don't really.
You would. Well,
want
if
to
you have
be
the
involved.
bubble, that's why you have the bubble. So
Right.
you're not destroyed. But you would think, though.
So the bubble just kind of
Yeah.
migrates in front of you the entire time.
Right. But if an alien was using warp technology to get here and stole Jay,
Mhm.
right? And they used warp technology, gravitational waves would be created from this, since black holes create gravitational waves. So we'd be able to detect that an alien took Jay in space. We'd be able to, if we're measuring for
Right.
gravity, we'd say, oh, wow, there's
There's
been
a
aliens
disturbance,
here.
right? Like,
Right.
because if there's ever a wave and something steps in the way of the wave, there's a shadow or some
Right.
sort of disruption in
We'd
the,
be
wave,
able
the
to
way the wave was moving, right?
Determine first whether they have warp drive, and second whether they took Jay or not.
Right.
At least, theoretically.
Theoretically.
I don't know. I don't know if you have any other formulas. I'm really enjoying our little math physics extravaganza, Mike. Newton's law of gravitational force.
I don't think I have anything
talked
here.
about this.
Right, we did talk about
No, we
this
didn't
one.
talk about is the timelines.
Oh,
If there was like a multiverse.
if he steps into a different.
Or what's a multiverse, Tony? Help me out here. We'll do some, Mike, why don't you do some Chat GPT and see what you can look up multiverse there.
Okay.
So, what's your theory? What's a multiverse, Tony? I mean, we all know whatever that those superheroes
ChatGPT?
guys. Sure,
Right.
those superhero guys. They
They did some multiverse. I don't
Mm-hmm.
know. My wife could probably explain it better than me because she watches those documentaries fairly often.
Mm-hmm.
But the idea is that you reach a point in time and you could go left or right, and maybe in one universe you go left, and in a different universe you go right.
Mm-hmm.
So maybe Jay is here in a different multiverse, and maybe he's not here in the one we're in.
If there's an infinite number of multiverses, right?
Yeah.
Then there's an infinite number of me's, and infinite number of where I'm not, and where I'm some form of me, and some
Mm-hmm.
Oh, that's just on a physical
or
thing.
infinite minus one if you're here in this multiverse. That
Sure.
one's already taken care of.
Then again, though, that takes it's. I don't know how God comes into all that. Is this summation of a me and every version of me part of the good bad decision? The
For or against God.
you chose like good free will and evil. The problem evil multiverse
Right.
here.
Right.
We're getting out of
Like
physics
there's
here.
a
but
potential
Multi-universe
or verse. There's
multi-universe.
a potential
Get it?
verse.
Multi-universe.
That would be the universe that you made. Of all your decisions, you made the wrong decision every single time. That's a pretty bad one.
But
That's a bad
at the
version.
same rate, though, I'm wondering if if I choose a good path, how that would affect all those other universes. Like, are they connected energy across the universe? You would think that they're not separate. They're all connected somehow, right? You would think that there'd be some connection between us
like
and then not us.
like a fabric texture.
I would think so,
Yeah.
right?
Yeah.
I also
Yeah.
think, just on a purely practical level, everyone out there, think about this. Everyone out there, if the world was made up of a bunch of yous, every person on this planet was you, okay, whatever, male, female, whatever, how would the world be? What would the world be like? Would you have war in your version? Because you're going to grow up as poor, you're going to grow up as rich, you grow up no parents, you're going to have all these different versions. How would the world be? Like, would your world of views, how would it be? Would there be war in your world, Mike? Can you foresee a version of you with all your, I don't know, sinfulness?
Yeah.
Where you could we don't live in a bubble. God gives us graces. There's
Sure.
angels. There's other forces that are, But just for kind of a thought exercise, could you see a version where I could think of like where sins or things of temptations where like, you know.
Yeah, but who would be tempting me but myself, right? My other
Well, let's say there was evil. Let's say Satan's in the world and he's tempting all the versions of you.
That's
And
not just me then. That's not just a world full of me's. That's a world full of me's plus.
Yes, that's
Satan.
what I'm saying.
Okay,
Yes, I'm
okay.
not trying.
So we
yeah.
are going that way.
We're
Okay.
going. Yes, I'm going that way.
Oh man,
Totally off topic, and I don't think we're going to find Jay in this. But I'd like to explore it a little further.
that could be tricky. You know, I have multiple consciences? Conscience?
I would say yes.
Consciousnesses?
I would say yes. It's an unfair thing because God created us all unique,
Mm-hmm.
and He created you with unique purpose. So it doesn't completely work as an analogy, but let's say yes. Let's say yes, but just let's say at this moment, suddenly you were transported transported in everyone's. Suddenly all these views come out, but you have the memories of that.
Of all of them?
Of all of them, you're different in all different places.
Okay.
You're different. You just Tony's suddenly in everyone. Suddenly you became that person. You're all over Tony's, right? Tony all over
All
Tony's.
the multiverse Tonys?
Yeah. Well, no, I'm not talking about the verse. Just our verse.
Do you look like Tony?
Yes.
Everybody in the world looks
Yes.
like Tony.
Yes, but it's not a big deal because
Okay.
you're just normal.
It's kind of like Oompa Loompas. Like
Yeah.
they're all the same.
Yeah, I guess let's not get too lost in the details. I'm just saying, like at that moment, and then you had the history. You remember your history, and it wasn't the history you had here. It's the history, like you grew up poor, you grew up someone beat you as a child, and
So in your example, I'm not just me, I'm all the people in the world, but all those people are me,
right.
different versions of me instead of,
Yeah.
oh, interesting.
No, I'm just saying. So, what is the world like? Are you? Do you think you created weapons to protect yourself? Like, are there versions of you that, do you think you create weapons? Do you have governments? What kind of world did you create out of yous? A bunch of yous.
I'm not sure, but I got an
Nature versus
important
nurture.
question here from
Sure.
one of our viewers. Was Jay last seen wearing a red shirt?
I mean, I'm wearing a red shirt.
Yeah, because the red shirt people usually don't make it, apparently.
Oh,
I'm hoping it wasn't because, I'm hoping we'll get Jay back.
Wow.
yeah.
Important
I'm not
physics
sure.
question.
You didn't really answer my question, Tony.
Yeah. I don't think I understood your question.
Did you understand my question, Mike?
No.
If you're a deacon, if you're preaching about this, like, what would the world be like if there were a bunch of yous in it? What kind of world would it be? We say, oh, yeah, I wouldn't do that, or if I was leader.
Right.
Now you're in a position where you're a leader. You're poor, you're middle class, upper class. Every situation you can think of, like you're hungry.
So based on me being brought up in all those different positions.
Yes, nature versus nurture. Was it, all right? If you were in a bad situation, would you, what's your level? You think of saints who can basically, I don't know, they wouldn't do anything to give up their faith. What level?
I don't think any of us would really make the world better.
No,
Right.
hopefully there wouldn't be war. I don't know. There'd be a lot. Well, then things create war. I don't know. I got off the topic. I know we're not going to find Jay with this, but
Yeah.
Yeah, I'm having trouble finding Jay with that. But I don't know. We got any other ideas on where we might be able to find Jay? Because
come look and see
I'm-
what
I'm
we
kind
had
of
on
Possibly
here.
fell off a cliff.
Oh, well,
I do remember that.
yeah.
We got a video of that.
You could.
Fortunately, he came back
Oh, he did?
Yeah.
And he came back.
Momentum,
Okay.
Impulse. What's
Okay.
impulse?
over on Mill Road Park.
What's impulse, Mike?
Oh, the impulse right
Yeah.
here is
I have those.
impulse is
Impulse power.
it's a change in momentum. It's a change in momentum, right? So whenever somebody or something has its momentum changed, that event is called an impulse. Like so.
Why? Why is it called impulse?
Jay could be impulsive.
True. He is
Yeah.
impulsive.
Yeah.
So what would go into him being
Impulse.
impulsive? What are the...
Well, he would need a force over
Force.
a period of time, any period of time, really small amount of time or a really large amount of time,
Is this
any size force.
is this centrifugal force or centripetal?
That's centripetal force.
that?
Centripetal force
Is that different from centrifugal force?
Yes. It's a center-seeking force.
What does that mean?
So it's the force that would keep an object in a circular path. So objects want to keep on doing what they're doing at all times,
Well,
right?
like-
So if you think
okay.
of a linear path, like an
Yeah.
object moving in a straight line, right? If something is pushing in that plane, in the two-dimensional plane of into and out of the board, right? Into and out of the screen, or in this direction here. If something's pushing in this direction and there's no other force pushing backward, it's going to accelerate in this direction, right? Okay. So we think of that acceleration being an increase in velocity, right? But velocity has two qualities about it. Velocity has magnitude, which is a size, like how much, but it also has a direction, right? So if somebody pushes on something and accelerates it in this direction, it'll change in magnitude, the how much, but it won't change in its direction. The direction is in the same direction it was going. It's accelerating by changing its speed, its magnitude of velocity. However, if something is moving in a straight line and you push it from the side, then you're changing not its magnitude of speed, but its velocity, but its direction. So it would
I'm with
move
you.
in a circular path,
As in
right?
an orbit.
So if
Right.
I tie a
Exactly.
string around Jay and I kind of do this, is that
That would be centripetal force. It's the
Centripetal.
force that is the center-seeking
That
force
keeps
of the
him-
circular path. Right?
Okay, so a space elevator, you know, like I have a yo-yo. Did we talk about this once?
No.
You know, I got a string and I got a yo-yo, and I get it up in space, and it's on the edge. It's attached to the planet, and it's super strong because I don't know what it's using, but and then the Earth it's spinning it around, right? Would that be centripetal force?
Yeah,
Would it?
it would be. Yeah.
So if Jay grabbed onto that, he'd get pulled up, or he would have to climb up.
Could he hold on to that? That
Jay's
yo-yo?
pretty strong, yeah.
I mean, would you be able to hold on to it? Would it be going? You'd be.
It would
I guess
hurt. If he was at the end of a string that's attached to the
he's
Earth,
up there.
and the Earth is rotating at
Wouldn't he be going at that speed?
1,000 miles an hour on the surface of the Earth.
He'd
Way
have-
up there, it would be
Right.
a lot faster.
But 26,000 horsepower, right? So wouldn't he have to have a ship that gets the same speed, and then he'd grab on? He'd be fine, wouldn't he?
He would be, and he wouldn't notice.
He wouldn't notice that he's moving.
actually moving, or the ship either,
Right, and then he could slide down.
because
Well, no, he wouldn't. He would have
He'd
to
have
start
to
walking down,
shimmy
down
or-
until it gets a point where
pull
gravity
his way
starts
down.
pulling him
Right,
more than
right,
the
right.
force.
Oh, that's
Right.
interesting.
Right.
So you wouldn't slide down. It'd be just like trying to move in any other
right.
direction where
Right.
you'd have to apply
Right.
force.
Right.
At some
go
point,
down.
wouldn't he be? It be shimmies down enough. There's a point. What is that point in the middle before? Isn't there some point where it's pulling on him this way? Right. Depending on how high the yo-yo part is, the end of it is. Isn't there a part where it's pulling him this way?
Well,
It needs to go
nothing
down.
pulling. There's nothing pulling.
Well, no, but it's when I have a yo-yo and it's coming around, right? There's force going this way out, right?
Right. That's what we, from a non-inertial frame of reference, that would be called centrifugal force.
Okay.
Right.
Wait, right.
Right.
But-
Which is not a force. It's inertia.
Okay.
But-
Inertia is taking you that way. Sure, it's not real force.
Right.
That's
right.
not okay. That's not at the
Right.
New York State Regions thing.
No, it's not.
'Cause it's
a
not
little-
real force.
It's not a real force.
I get it. I
It
understand.
depends. Like, so if you're in a car, if you're in a black box, like
Mm-hmm.
you can't see outside, and somebody's swinging that black box in a circle, you're going to be thrown up against the wall,
Mm-hmm.
right? And you assume there's a force on you that's throwing you against
Okay.
the wall. But really what's happening is your mass wants to keep doing what it was doing, and that is moving in a straight line, but you keep changing.
Right. I got
direction.
that.
Yeah.
Okay, but so maybe we don't have all the physics down here, right? Because assuming you're on the end of that thing,
So
you're going to be flying. It's going to be whipping you, right? It's going to be whipping you around. Like, but okay, there's a point where we said we had to shimmy down. Well, why would you have to shimmy down if there wasn't force against you? The only reason to shimmy down is there's a force against you that you have to kind of get down. You're going to get to a point where there's equilibrium between the gravitational force and the
and-
centripetal force.
Centrifugal force.
Centrifugal, right? There's a
Right,
point
right.
in the center where they're equal.
Right.
We talk about two
I
forces, two
imagine.
masses.
I mean,
So if you go up here,
where
there
your
is.
inertial mass and your gravitational mass are the same.
Wouldn't you think it'd be hard to hold on to that yo-yo thing in the sky? Wouldn't it be hard? Like if it's far out, It's got to be far enough.
It would be really hard.
You'd have to be far enough where the weight of that big rope, like there's that weight.
Right,
You have to
because-
be high enough so it can stay up high, right? Where it's far enough so it creates enough
It makes
tension.
sense. It makes sense. Yeah,
I would think.
But the weight, like you said, the weight is force, right? It's
It is,
gravitational
right?
force, right? So you would have to consider the mass of that string too, which would be an immense
That would be
size,
immense, unless
too.
it's like graphene type things,
right.
something really light and super strong.
We haven't really figured out how to use those yet.
No.
But if Jay is up there, my question is, how long will it take for him to climb down? Because we're off next week, but in 2 weeks, Jake is going to be on the show, and I'm hoping he'll be able to climb down by then.
He would need some sort of breathing apparatus. Assuming he's not in energy form, and he becomes a
Right.
J form, he would need some sort of
Right.
breathing apparatus, and he would need some sort of pressure. I mean, if you're up high, you need
Yeah.
the pressure in your body. You need a suit so you have pressurized. Otherwise, your guts are going to
Yeah,
blow up like a balloon. You're familiar with all
I'm
that,
sure Jay would have brought that with him.
right? He would have.
So I don't know. Do we know how far that is?
Well, you'd have to be. It
Is
depends
that
on
60 miles or whatever up to the.
I'm guessing. Depends on the
So-
weight, like Mike said.
Right.
The weight of the. I mean, if he had the space elevator, would be the
equilibrium.
idea of you'd want to be able to.
But is it diagonal or is it straight down? I think it's diagonal.
Well, it's kind of because it's being dragged.
Yeah.
Would there be a little bend?
Mm-hmm.
Would there be a bend,
There
or
will
would
be, yeah.
it would be right? It
So
would
let's
be
say it's 120 miles, just
okay
to make
sure.
something up.
Okay,
Can Jay travel down a space elevator rope 120 miles long in 2 weeks with breathing apparatus to get here in time for the next show?
possibly.
Okay.
Possibly. I mean, he could just take the space
Okay.
elevator. Assume they made this. I think they would have the elevator go up and get him, and maybe that would be the fastest way to do it.
Okay.
We may have to leave it there.
Yeah.
But I want to thank you all for watching Issuenite. This has been great. Physics, Mike, thank you so much for Regis physics. I'd like to have you back for math. Do you teach math?
No.
Chemistry?
Yes.
I don't like chemistry. You got any other subjects?
Biology.
Oh, I'd be interested in biology. That'd be good.
All right.
We could do it from a biological angle. I'm not
Biological,
sure.
yeah.
Okay. All right. Well, thanks for watching Issuenite. Come back sometime and watch us. We love you. And I'm not Jay. I really need Jay to be here.
Yeah.
All
We
right.
missed
I
you.
do.
Issuenite. I don't know where's the Issuenite logo.
You
I
gotta
can't
fade
find
out
it. I
your
guess
logo.
I'm just
We
gonna
don't
hit
know
stop
what to
here. I don't know
do.
what to do
We
here.
missed
Stop
so
streaming.
much.